Just like in the simple linear regression model, in multiple linear regression model, we try to explain the variation in y in terms of variables x1 and xk. Yeah, if there are k variables, so y is the dependent variable or outcome variable, beta 2 is the intercept, beta 1 is the slope parameter with respect to x1. x1 is the independent variable, just like x2 and xk variables. They can also be called explanatory variables, regressors. U is an error term. And in time series models, we tend to call these disturbances, or they are simply unobservable variables. So if we cannot collect data for certain variables, they are usually in the U, so we don't include them, right? We cannot observe them. If we cannot explicitly include them, they are most likely to be here in the U. And we always hope when you run a regression that these variables that are not included in the model do not correlate with any of the included variables. And this is the summary of the dependent and independent variables. Motivation for multiple linear regression model. We can hold explicitly are the factors fixed. We can also include more factors, and we can allow for more flexible forms. For example, holding other variables constant case. We would like to estimate the return to wages, or return to education, I should say. Let's say that on the y-axis we have wages, let's say hourly wages. Beta 1 captures the effect of education, number of years in education, on wages, holding everything else constant. Yeah, and experience is just the number of years in the labor market, and U is all other variables that are not included here in the model. If we did not include experience in the model, this would have been part of the U. Yeah, this could have been part of the let's say U tilde or maybe E, let's say. Yeah, then usually experience is correlated with education. As a result, beta 1 or estimator here will become a biased estimator. So with the multiple linear regression, we can explicitly hold experience constant in this case and estimate the effect of beta 1 on education on wages. Yeah, and we still have to assume that those variables that we included in the U do not correlate with experience or education. Yeah, so the expected value of errors conditional on education experience is basically 0. So in other words, they do not correlate. What if we are omitting variables? Well, here is another example. So this is the average score, standardized test score of schools. And this variable here, expenditure variable, is expenditure per student at the school. And this is the average income, average family income of students at this school. Notice that in the USA, districts with good schools usually would have rich families. Incomes will be higher in these districts, tax payments will be higher, and higher taxes means higher spending per student. So let's assume that we estimated this model without the average income included. So as a result, average income would have been in the U. Let's say this becomes an E. So we also know that average income is correlated with expenditure. Yeah, so there is kind of positive correlation, strong or weak, there is a correlation. If that's the case, and we don't include the average income in the model explicitly, we would expect the beta 1 to be biased. So average income would have been an omitted variable, and we would have an omitted variable bias here. But fortunately, we can measure the average income per family in the district, for example, and then include it explicitly in the model. As a result, we are now able to estimate the expenditure's effect on average score, holding everything else constant. Yeah, so that's the benefit or advantage of having running a multiple linear regression model. Another motivation or advantage of using a multiple linear regression is that it allows us to form complex multiple linear regression models, or it offers us flexibility in the form of modeling. Yeah. So for example, let's say this is the consumption, family consumption as a function of income and income squared. Now the idea here is that, so if I draw this here to give you a brief idea, so this is consumption and this is income. We know that as our income rises, what happens is that we do consume quite a bit, yeah, but as we become richer and richer, we don't continuously sort of monotonically consume as we increase our income, yeah, as our income increases. Instead, at some point the increase will taper off and maybe it starts diminishing, yeah. So we could expect such behavior, yeah. This is in fact the behavior, empirical behavior looks like this, rather than the consumption going monotonically increasing this way, yeah. So since this is not a linear sort of we cannot fit a linear model onto this sort of behavior or relationship accurately, we should be a bit more innovative and come up with an idea that captures this sort of bend here, yeah. This parabolic equation would capture this case here. So as a result, we may expect beta 2 to have a negative sign here. The main point here is not that it's negative or positive, it's that we will be able to better describe consumption in relation to income, so by including a square term of income. So with the multiple linear regression, that is a possibility. If it was a just simple linear regression, we wouldn't have this term, right? This term would be part of the U, yeah? So it wouldn't have been included in this model, and then we would simply fit a straight line like this on a, so like this, for example, yeah. With this model, the interpretation is slightly different. For example, the effect of income on consumption is calculated using this expression here. What it means is that then the change in consumption with respect to income, or when the income changes by 1 unit, we cannot hold income square constant here, because when we change the income, well, income square will also change, yeah. So instead we use this expression here to estimate the effect of income on consumption. So in that case, we would need to know the starting or original income level here. Then we just plug in the number here, income level here, then the estimated beta 2 times estimated beta 2 plus times the income level plus the beta 1. Then that gives us an effect of income on consumption. Here is another example of flexible forms in multiple linear regression modeling. Notice here that it's a log salary, so it's the salary of CEOs as a function of sales, then tenure of chief executive officer plus the square of executive's tenure here. The very interesting case here is that the salary and sales has a sort of constant elasticity relationship or log-log relationship. So this is kind of one function. And then you have another function with the salary and tenure is basically has a quadratic relationship, yeah. So there are two functions in one here, which is nice, isn't it, with the multiple linear regressions. The relationship might look like this, for example. So as the tenure increases, there is an higher increase in the salary, but then that increases diminish eventually, yeah. We don't expect a linear kind of increase in salary as the tenure increases, yeah. That's not the case here. Empirically, it's sort of what we call the parabolic relationship here, yeah. So we need to, in order to capture this such relationship, we can with multiple linear regression create this sort of two-part kind of formulas and then put them together to form a multiple linear regression. One important thing is that even we have squared terms here and log variables, our relationship between salaries, sales, and tenure is basically linear, yeah, because the model is linear in its parameters. Now briefly about the interpretation of multiple linear regression model. I have already mentioned about this, the interpretation of multiple linear regression model, but briefly, with this formula we can estimate the total effect, basically change in beta 1, change in the dependent variable. Predicted dependent variable is basically the kind of weighted sum of changes in x1 and x2. So beta 1 hat and beta 2 hats are the weights, estimated weights, the effects, yeah. So this is the total effect. This is the total effect, yeah. But if we would like to estimate the partial effect, then we have to hold x2 constant. So that means we assume that change in x2 is 0. We can then isolate the effect here in this formula, and then a bit of manipulation leads us to this case, yeah. Here is an example about the partial effects. Let's assume that we would like to model college GPA as a function of high school GPA and an ACT. Now, as you can see, holding ACT constant, 1 point increase in high school GPA results in 0.45 points change in college GPA. Yeah, and in this case, we assume that ACT doesn't change and everything else doesn't change here, right? Anything that we included or not included will not change. It's just the isolated effect of high school GPA on college GPA. Now, in this case, we're assuming that if we had two students with exactly the same ACT scores, this would be the effect of high school GPA on college GPA in case one of the students had a 1 point higher GPA, yeah? So if one of the students has a 1 point higher high school GPA, their college GPA would be this much higher, yeah, relative to the other student whose GPA is 1 point lower but has the same ACT. So that's the idea here. Just like in the simple linear case, our goodness of fit measure R squared is the same, works in the same fashion as it worked for simple linear regression. Yeah. So here in this case, a little bit about the mechanics of R squared. This is actually total sum of squared. So SST sum of squared total or total sum of squares. So just to keep consistency as with this and this case here, yeah. So this is just a typo. Let me just quickly draw here so that we have the intuitive explanation as well. Y, X. Let's say the Y variable mean of Y is described by this line, and let's also assume that there are these are data. They and then describe it or fitted data around the fitted line. Let's take this point here. This distance here would be then the residual. Yeah, it's the distance between the actual data and then the point here that is predicted for this data point. Then this distance here is the difference between the mean value and the fitted value. So you can think of this point, for example, y bar, while this is y hat. Yeah. Now notice this. Now sum of squared total is basically the difference between the so let me just put this down here as well, y itself. Yeah, this is the actual y here. Yeah, so sum of squared total, so total sum of squares is the difference between the mean y and then individual actual points squared and their sum. Yeah, so it's the sum of squared total, or total sum of squares I should say. Yeah, that's this distance. This distance here in this case is the difference between fitted point and then the mean, yeah, actual mean point. So that's this long distance here. So this is the sum of squared or explained sum of squares. Then the distance here between the fitted point and then the actual point u hat, well, that's the residual. So residual sum of squares is then this value here. So u hat squared and sum. Yeah. Now this should make sense now. Where what R squared what R squared measures here. So total sum of squares is basically explained sum of squares plus sum of squared residuals. Yeah. If we do a bit of manipulation, it gives us this R squared formula. Explain sum of squares over total sum of squares, or simply 1 minus residual sum of squares over SST. So 1 minus whatever not explained by the regression divided by total variation. Yeah, here. So whatever not explained divided by total variation. As such, what we mean here is that if the SSRs are high, then we can expect 1 minus this expression to be a low value. So as a result, we get a low R squared. Or if I draw the case where low R squared happens, is that we get these points much further away from the fitted line. Yeah. Yeah. So the R squared in this case will be low. the points will be away because the sum of square residuals, or the residuals, individual residuals, will be higher, and higher residual squared will become even higher, yeah, values. So as a result, we have a poor fit to the data. But if the dots are very close to the line, like in this case, dots are very close to the line, or relatively closer to the line, then we would expect 1 minus a small value here, yeah, because SSR, the numerator, will be small. As a result, this whole ratio will be small. 1 minus small value gives us a higher R squared, yeah. Here the R squared is higher, while here the R squared is a little lower, yeah. So alternative expression here is given using this complex formula, but that's actually simple. Again, notice this, it's just the correlation, covariances between variables, yeah. So we'll skip that. Usually we would use in practice for empirical studies adjusted R square in multiple linear regression instead of an R square. Now mechanical interpretation further with an example here. So here is an example explaining arrest records. So here the dependent variable is number of times arrested in 1986. So a person arrested, number of times a person is arrested in that year. Then this variable here is the population, or the proportion, I should say, of previous arrests that led to convictions. So once a person is arrested, the person may or may not be convicted, but it's the proportion that led to the conviction. Now it's the number of months a person is in prison in 1986, and this is the number of quarters that person was employed in 1986, and we're trying to see if number of times person arrested can be explained. Why, let's say maybe why large number, some people are arrested so many times, for example, yeah. So we're trying to see the determinants of this factor here, the number of times a person is being arrested, yeah. So it turns out that taken together, let's assume this way. So taken together, these three variables as a model do not explain much of the variation in arrest numbers, yeah. So basically, only 4.1%, yeah, approximately 4.1% of variation in this variable, the number of times a person arrested in 1986, is explained, yeah. Only 4.1% is explained, taken together by this model, yeah, jointly by these variables. So well, remaining 95.9% is then explained by other variables that are not included here, which usually end up inside the U, yeah. In a population model, it would be in the error term. So what it means is that the line here will be poorly fitted, yeah, into the data. Let's now talk about statistical properties or assumptions for the multiple linear regression model. Some of the assumptions are simply borrowed from simple linear model. So we'll start with the first one. As in the simple linear regression model, we expect, or we assume that the model is linear in parameters, which then means as long as the parameters are not in squares, has some exponent, or in some sort of ratios, then this is a linear model, yeah. For example, model of this type. This type would be a non-linear model because of this non-linearity in the parameters, yeah. Now we also assume that the samples we draw from population are basically modeled using this population model, yeah. All the variables are randomly sampled. We would like to then estimate the beta 1, beta 2, beta 1, and all the betas, assuming that the data comes from the population that follows this equation, yeah. It was generated using this population equation. Assumption number 3, this is an addition now to the original simple linear regression model assumptions. So there is no perfect collinearity, or the explanatory variables are not perfectly correlated, or there is no strong correlation. Let's put it this way: there is no strong correlation between the x's. So if we had y being modeled as a function of x1, x2, x3, then none of these is the linear function of the others. So there is no perfect collinearity between these variables. But imperfect collinearity is fine as long as the variables are not strongly correlated. Similarly, we also rule out the constant variables. We don't want variables that are not changing at all, because this will then lead to correlation with the constant in regression model. So further examples here related to the multicollinearity case. For example, average score. This is the standardized test score that we discussed earlier. So average score is a function of expenditure per student and average family income. In small samples, there is a possibility that average income is strongly correlated with expenditure, because remember, expenditure per student is a function of tax, and tax depends on average income in for example, districts in the USA. So high income districts means high tax. That high tax basically increases the budget of the district or the state, let's say. Then they usually spend more on schools, or spending will be higher per student. So there could be in small samples a strong correlation between averaging income and expenditure. In this case, this would create a multilinearity or some sort of near perfect collinearity in small samples. And the OLS will be confused then. So it tries to disentangle the effects of these two, but it will not be able to do that. As a result, we end up having higher variances in associated betas here. In large samples, the correlation will not be as strong. So in that case, this model will be fine, but in small samples, there's a risk of this multicollinearity. Now moving on, I have another example here. This is an interesting one. So let's say usually in the USA you have two candidates, candidate A and candidate B, and their campaign spending really is crucial for the voter outcome, or the outcome of the voting. For example, share A is a variable measuring the share of spending or campaign spending by candidate A, and share B is a measure of spending or proportion of spending by candidate B in their campaigns. And share A plus share B is equal to 1. So if there is total spending, given spending, then we simply here split them into share A, share that's due to the candidate A, and share that's of candidate B, right? So the sum of the two will be equal to 1. This can be written as share A equaling 1 minus share B, for example. So this is share. In this case, share A is a linear function of share B. So if we put this together in a multiple linear regression, we certainly get a very strong, in fact, a perfect collinearity. So we should avoid in such cases, such situations, and before we run the regression, we must make sure that our variable is not a linear function of any of the included other variables. Here is another example. Now, what if we are looking at non-linearities in the data, not the model, not the parameters? So this is fine. This is a linear model. This is also a linear model. However, only this one can be estimated, because income is not a linear function of income squared. Here the relationship is non-linear, which is fine then. So income is just squared, becomes the non-linear function of income squared. However, this case is not the non-linear situation here, because log income can be a function of linear function of income squared in this case. Notice this, how it works out. Log income, so it's squared. And if you remember from your calculus, so it's going to be 2 log, I can rewrite that as income in this form. So this clearly is telling us that the log income is a linear function of log income. It's basically log income is equal to 2 times log income in this case. So we cannot estimate this regression model. This next assumption, as in the simple linear regression model, tells us that conditional mean of the errors is equal to 0. What it means is that the errors and then included explanatory variables are not correlated, yeah? They are independent, in other words. Let's take this case here. When we estimated the effect of expenditure on average score, we included or controlled for average income in the district. Now notice that if we did not include average income, if we weren't able to measure average income, then it would have been part of U. And we know that expenditure, to an extent, is a function of average income. Not including the average income here would violate this assumption. Now, this is a culmination in our discussion here. So, assumptions 1 through 4 taken together allows us to state that expected value of beta, let's say j hat, is equal to beta j, or OLS is the unbiased estimator of so this is OLS estimated beta j hat is the unbiased estimator of the population parameter. Yeah, so what this means is that if we take many samples, let's say lots of samples here, and of course with replacement, and estimate beta 1 hat, beta 1 hat star, beta 1 hat star star, and so on and so forth, many of these samples, yeah, if we estimate many of these samples and put this in a density curve, or estimate what we call this, build their empirical distribution, then the average value of this empirical distribution would be, so this is beta j hat, would be equal to the population beta j. Yeah, so on average we will hit the population parameter. When we say that there's a biased estimator, OLS is a biased estimator, or our estimator is biased, or estimates are biased, we mean that the procedure with which we calculated these estimates is biased. So it's the procedure, OLS in this case, would be biased. When we say we have an unbiased estimator, or OLS is unbiased, we simply mean that it's the OLS procedure that's unbiased, not the estimate. So if we get an estimate of beta 1, we cannot say unbiased estimate, but we can say unbiased estimator, which means the procedure, OLS procedure that we applied across all possible random samples is unbiased. So far we talked about omitted variables and possible biases as a result on our estimators and estimated values. Now how about if we include an irrelevant variable? Well, it turns out it's not a serious problem, or at least is not as big a problem as in the case of omitted variable bias, but we should try to avoid including variables that are not relevant, that do not have significant effects. So essentially expected value of beta 3 hat here is just 0. In other words, x3 doesn't have a significant effect on y. So that should be one sort of indication of irrelevant variable included in the model. So we usually drop it in empirical exercises. So however, if you include this variable, still you would have possibly you would have an sampling variance, yeah, higher sampling variance, I should say. So the standard errors will be unusually higher than when this variable is not included. Yeah, so try not to include them. Now, what if we exclude the variable? So we discussed that earlier, that this will lead to an unomitted variable bias. This is more of a serious problem here in this case. So let's give an example of that situation. So this is the true model. This is a true model. So true model states that y is a function of x1 and x2, and beta 2 and beta 1s are population parameters. But instead, we, let's say, dropped this variable. We omitted this variable and estimated this part. Then in that case, this would be our estimates. Yeah, this would be our estimates and predicted values. So y tilde is equal to beta 0 tilde plus beta 1 tilde x1. If the excluded variable x2 is a function of a linear function of x1, so let's assume that x2 is correlated with x1, but x2 is dropped, as you remember from our previous slide. So if we plug that into x2 here, we get this little longer sort of expression here. Then the model itself is plugged into the original population model. So this population model should be written in this form. Just for exposition, I'm going to put this down. We don't need that last part. So instead we will have the U. So this here is basically this thing. Yeah, I'll just plug that into this original formula, population model. And if you open the bracket by multiplying beta 2 through, what happens is that then you have beta 2 times sigma 0. That's a constant, which is now is a part of the original constant now. Yeah, so now this is a composite constant. And then you have beta 2 times sigma 1 x1. So then if you collect the similar terms x1s, then you get beta 1. So this is beta 1 with a bit of bias. So in this case, this is the bias amount. Yeah, and this is obviously then with the nu and u being error terms, beta 2 nu plus u gives us a composite error here. Yeah, so as you can see, when you omit a variable, important variable from the equation, you will have biased estimates, or all estimates in fact are biased here, right? So beta 1 is biased, and sorry, this is beta 0 biased, and main variable beta 1 is also biased, and the bias amount is that much, beta 2 sigma 1. Sorry, in this case it's a delta 1 rather. Now assumption number 5, it's similar to the one we discussed before in simple linear regression. It's the homoscedasticity assumption. And if you remember, with the homoscedasticity assumption, if we draw, let's say, in a model like this, it would be useful to draw this anyway. So let's say these are errors. So we expect the errors to have a 0 value here. As the x's change, as the x values change, we would expect, or we assume, that OLS generated errors I should say residuals in this case, yeah, basically constant, yeah. So if we were to put two bands, upper and lower bands, the residuals are within this range, yeah. They don't exceed the range, or they don't cross the range, or drift away from this. They stay within the range, yeah. However, this assumption may be easily violated in cross-sectional analysis, and we may see some errors over time, or not over time, across x values, yeah, some higher x values to go, let's say, outside the band, yeah. They could expand in this fashion. So in that case, notice this, the distance here is higher than the distance here. So the variance at this point corresponding to, let's say, xn is higher than the variance here. So we cannot assume that the variance in that case is constant, yeah. So this is a violation case here, that a sigma squared is simply a sigma I squared as a result, yeah. So, or that's not the case, yeah. We are now in a position to state the variance estimator, yeah, OLS variance estimator here. This is the formula with which we estimate the variance of the OLS estimator. Now we assume that multiple linear regression assumptions 1 through 5 hold. If any of these assumptions is violated, we will not be able to use this formula to estimate the variance of the OLS estimator. Now here it's important that we assume that the variance of u conditional on all the x's, included x's, is basically sigma squared, yeah. This is important because we have in the numerator this variable here, the variance of the error term. Then we also have this SST here, total sum of squares, and 1 minus rj square. Notice this rj square is not the r squared of this function. So we have a function, let's say beta 0 plus beta 1 x1 plus beta 2 x2 plus u, yeah. So this r squared here is not the r squared for the whole model. Instead, it is the r squared, for example, for x1, yeah. Let's say we want to estimate the variance for beta 1, variance for beta 1 estimator. In that case, sigma squared will be the error variance for the whole model over SST using the first x1, let's say, times now 1 minus r squared 1. Here the r squared 1 is from this equation, is a function of beta. So this is now alpha 0 because betas have been used here, plus alpha 1. So in this case it's x2 plus, let's say, nu, some nu. Yeah, that's an error, nu. So the r squared is the fractional variation that the x2 explains in x1. Yeah, so it's not the r squared that we use for the model, actual models. Notice this, errors are in variance of errors are in the numerator. Yeah, numerator, which means higher the error variance, higher the variance of the estimator. So we would like, in fact, to get a lowest possible variance. So we would like to get the error variance the lowest as possible as well. Yeah. So estimates will become imprecise if the error variance is high. Next, we have total sample variation. Yeah, this is total sum squared is the sample variation. Now, if this is high, what happens is that the whole ratio will be, if this is large, I should say, if this is large, the whole ratio will be small. Yeah, so we would like to get as much variation in our sample as possible, such that the estimated variance of beta 1 is lower. Yeah. Similarly, we would like to have a small 1 minus rj squared. Yeah, we would like to have, so in this case, high, I should say, high, because let me write this down here, variance of beta 1 squared. This is for beta 1, let's say, sigma squared over SST1, 1 minus r1 squared. Yeah, so we would like to get this thing as high as possible. So we want this part of the equation as high as possible, because when that is high, then when you divide a small number by a high value, you get a very small number as well. Yeah, so what it means is that if this is small, if r1 squared is small, in other words, x1 is not related linearly to x2, then this would be small, and then 1 minus a small value will have a high value times a high value gives us a sort of high product here. Yeah, high value out of this product. Then a small value divided by a high outcome will give us a small variance. Our intention is to get the smallest possible variance. Yeah, so here is a sort of graphical explanation of what I mean. So variance of beta 1 hat increases as the r squared, this r squared increases. Notice this, to an extent there is a linear relationship between the variance and then the r squared, but from this point onwards there is this exponential increase. It turns out when the r squared, so by the way, this line here has the highest value of 1, so this is exactly 1 here. So if the r squared, r1 squared in this case, approaches 1, which means x1 and x2 are correlated, then there is a multicollinearity. With a multicollinearity, the variance will always inflate. Yeah, so there is a variance of OLS will inflate. So when this is high, 1 minus a high value will give us a very small value here, and a very small value times the SST gives a small number. So a number divided by a small number, as you know, is kind of is giving us a high number. Yeah, that's when you divide a small numerator by a very small denominator, you will have a large variance in this case. Yeah, so the variance explodes as a function of r1 squared here, right? So we have to be careful when we empirically estimating OLS models, and we have to check first if there is any correlation between the two, and if there is, then we will have a high variance of OLS. In fact, well, if you forget to check in your analysis the relationship between, or correlation between x1 and x2, then you may notice that if there is any sort of correlation, it would be captured by variance of beta 1 hat or beta 1 betas. Yeah, so you can easily check that way as well.